Hi, my name is Misha Hay. I'm an analytics practice lead for NV5 Geospatial, previously known as Quantum Spatial. We are currently going through a rebranding, and so you'll see a mix of logos throughout this presentation, but let's remember that they are the same company. Today I'm going to be talking about some of the considerations and complexities of elevation-derived hydrography to support the 3D National Hydrography Dataset. So we're going to cover data consolidation and management, data schema development, the capture specifications, open water delineation, geomorphic indicators, hydro enforcement, line work derivation, feature smoothing requirements, network integration and finalization, stakeholder review and feedback, some of the other considerations. And we're not going to go into a lot of detail. These are all going to be pretty high level overviews of these various components. So the source consolidation and management is the start of the process in our mind. It's really gathering all of the data that you might want to feed into this hydrologic network derivation process. So it includes the source data like LiDAR points, lines, and rasters, digs into the USGS, NHD, and WBD datasets, the NWI dataset, adds roads and rails if available, finds an authoritative ortho imagery source, and downloads any state or county culvert databases that might be available for a particular location. Each of these is first evaluated for currency, accuracy, completeness, and agreement with all the other data sets, and then arranged into processing blocks. We typically use a HUC12. We find those to be most manageable, both for the processing chain and the manual intervention process components. We buffer and clip and reproject and standardize to make sure that everything is going to agree at the end when we piece all of the HUC12s or whatever our processing block is back together. And this method really identifies any shortcomings or discrepancies in the source or ancillary data sets at the beginning. The data schema development is another component we really want to tackle right at the onset. So the NHD schema for USGS is well defined as far as classification rules and capture rules and topology requirements, data agreement, but it differs a little bit from the EDH schema as far as F code usage versus E-code usage, I guess. And then a state might, or a locality might have additional information that they want incorporated in their network development or preserved from any previous work that's been done in the state. So we build an integrated data set accounting for all of these various needs of the different stakeholder groups, and then build some automated scripts to convert that integrated schema into either a state or locality specific or for upload into the National Hydrography Dataset. So the capture specifications are pretty detailed as far as agreement with the source data, the density of features captured, the vertex alignment, the topological consistency, is all pretty well defined, but it's strict and needs to be adhered to and be very well understood by the vendor or partners that are going to do this work for you. This is very different than previous hydrography data sets, which were based largely on photo interpretation. And so understanding those specifications and having a method to address them is really going to be essential for anybody doing this work. In our opinion, this requires at least some degree of automation for both the derivation and QC in order to preserve the topological consistency and make sure that everything that should be captured is being captured and correctly. The first part of this for us is to delineate the open water. This is a relatively old slide, but the concepts remain the same. We use an object-based image analysis rule set I built in eCognition. The specifications between the LiDAR break lines, which is a 2 acre minimum capture threshold, and the NHD, which is a 1 acre minimum capture threshold, is most likely going to require additional open water delineation relative to the national or relative to the LiDAR-derived break lines used for hydroflattening. Our process relies on terrain descriptors and LiDAR descriptors to develop homogeneous objects, and then it uses a kind of a seed grow approach where we find known water and then grow those out based on terrain characteristics. There is some promise in the convolutional neural network side of things to delineate these in a more efficient, let's say, fashion. But the behavior of LiDAR off water, as many of you know, is really erratic and can have anywhere from, maximum returns to no returns and anywhere in between, and likewise for the intensity of those returns. And so that's where the terrain descriptors are really informative. We deploy a suite of geomorphic indicators for direct channel detection. They're listed there on the left. One of the primary ones is the geomorphon classification, which is perhaps the most intuitive, which classifies and delineates the landscape into the features there you see in the legend. This can reduce the overall processing burden as well as be very helpful in the QC process, identifying both omission and commission errors. Hydro enforcement, another big component of this, network derivation. So it's an iterative process to remove false obstructions to flow. LiDAR doesn't really see culverts, it sees the roads that the culverts go under. Again, this is an area where deep learning and convolutional neural networks are showing a lot of promise, but because this is an 85% classification of these areas is not actually sufficient to meet the standards, it still requires a lot of manual QC. And so we have not found machine learning to be a huge advantage as far as reduction of labor accuracy, because it still requires us to look at the entire data set. But again, promising, and the detection of channels or sinks on either side of a culvert or false obstruction is likely the most promising component as far as doing the research into the deep learning side of things. So the basic stream derivation process relies on flow accumulation and direction. This is just an ArcGIS graphic that shows which direction each water will flow from each cell to another, and then summarizes the accumulated flow across the entire landscape. We consider this an iterative process because we'll run through the flow direction and flow accumulation, we'll look at the stream networks, we'll hydro enforce new areas, we'll iterate the routine, we'll look at the geomorphic indicators for omission and commission, and then rerun through the process. But at this point, we now have automated flow lines that are ready for a full manual QC, and editing is necessary. There are other approaches to tackle this. We have not found them to yield sufficient accuracy and topological agreement to meet the USGS standard, but it is a big area of research right now. As I said, LiDAR behaves very erratically off water. So there's an elevation line that you can see in the red there, just a profile off the DEM. And there's a lot of jogs and bumps and ditches, but the hydrologic network that we're deriving this from needs to be enforced downstream, so all those jogs and bumps need to go away. Likewise, any change that is made on a single line needs to be propagated throughout the entire network, both for double line streams, single line streams, and any water bodies that they intersect. Just another example of erratic behavior of LiDAR on a stream channel. And the XY smoothing is the sort of the other component of smoothing that needs to be tackled. So you can see there in the no smoothing block, you have very jagged lines going cell to cell. It's a raster artifact of the flow direction flow accumulation process. But the typical smoothing processes available in ArcGIS and others create nice aesthetic lines, but can pull the river channel or the line work well outside of the actual river channel, which is not going to meet the specifications. So I wrote a relatively simple raster removal process, which preserves the line work, reduces the vertex density, and creates more aesthetically smooth look and feel of the final line work. All this stuff needs to be tied together. So we have our polygons, we have our double line streams, we have our flow paths, and all of those things need to be integrated. So this is another place where automation can really help preserve the topology and reduce the overall manual effort by automating centerline or artificial path development at the inlets and outlets, enforcing the line direction correctly. And then this allows us to feed the whole integrated network back through the elevation smoothing or agreement process to make sure that any changes made anywhere in the network are propagated throughout the entire network. This also allows us to ensure that features are classified correctly. So, we don't have streams entering a pond that are not classified as artificial paths. Underground connectors can be readily identified based on our hydro enforcement process. And so, again, this is an area where automation is going to really reduce the errors and manual effort required to meet the topological specifications of the National Hydrography Dataset, and likely what anybody will want for their state or local datasets. One thing to consider as states and localities embark on this process is in a heavily urbanized environment, the surface flow really isn't the primary hydrologic driver. This is a project we did in DC to integrate their combined sewer overflow network. And what we were able to do, the remote sensing can't actually detect the subsurface network, but most municipalities have this stuff pretty well mapped. And so we were able to integrate the subsurface network by identifying all of the inlets at which the surface flow will enter that network, and then all of the outlets. And then we're able to trace back up from the outlets to the inlets and identify what we're calling sewer sheds. So basically areas that all feed a unique combination of outlets. In DC, it was a one-to-one and many-to-many and many-to-one kind of relationships. And so this was quite complicated, but really depends on what urban landscape you're working in. But this might be something that a state or locality wants to have integrated. There are schema concerns as far as feature density. It actually breaks the rules of the current rules of the NHD. And so we had to build sort of one data set to give full resolution for the city of DC, but another data set with a reduced resolution or a reduced vertex density that really just identified the major flow paths so that it could be ingested into the National Hydrography Dataset. Stakeholder engagement, whether you're doing subsurface flow or not, is incredibly important. Right now, there's really no modelable relationship that accurately classifies periodicity. And so that's one of the big components that we need to preserve from the previous data set, but also like the previous National Hydrography data set, but also a really great opportunity to let your stakeholders with real on the ground knowledge help to classify periodicity of particular streams, as well as potentially identify any spurious underground connections. We can detect a lot from LiDAR, but as you saw in the previous slide, there are underground connectors that we just don't know what's going on, and so that's where the local knowledge really comes in. And so to deal with this, we build a web interface and allow everybody who's involved in the project to go in and add comments, redraw lines, identify periodicity or potentially other features that you might be interested, as far as whether something is fish bearing or whatever a state happens to need. So being able to develop a system to record and ingest the local feedback is really going to improve the utility of the overall project to the user community. And then one of the final things to consider is, the NHD is just one component of the hydrologic landscape. The National Hydrography Dataset is another one, and they even have overlapping features. And USGS and Fish and Wildlife, NRCS and FEMA are really starting to have conversations about how to unify these data sets and how to build a single authoritative picture of hydrology for planning and tracking purposes. So if a state or locality is thinking about updating their NHD, it might also be a great time to update your national wetlands inventory or your wetlands inventory data. And then if you are in a flood-prone area and are considering updating those maps, again, a unified authoritative picture is probably a good thing to think about. It obviously has funding implications and expertise requirements, but it does seem to be the direction that the community is going. With that, my name again is Misha Hay. There's my brand new email as of today. And Andrew Brenner is the Senior Program Director for our hydrology group, and his contact is there as well. Don't hesitate to reach out if there are any questions or you'd like to discuss further. Thank you.